Hello students, today we are continuing the oscillations and our today's topic is energy in simple harmonic motion. As we know, a particle which is executing a simple harmonic motion is also concerned with a type of energy, and its energy will be the mechanical energy, that will be the sum of its kinetic energy and its potential energy at any position in simple harmonic motion. Let us consider a particle executing a simple harmonic motion is concerned with kinetic energy and potential energy. Its total energy will be the sum of kinetic energy and potential energy, and energy here is function of time and is periodic. We have already taken an expression for the velocity of the particle executing a simple harmonic motion as a periodic function of time such that its velocity as a function of time is equals to minus omega a sine omega t plus phi. As you know here, the Vt is the time varying function of the velocity of particle executing simple harmonic motion. Omega is the angular velocity, or you can say the angular frequency of the motion of the particle. A, the maximum amplitude which the particle traces, and sine omega t plus phi, which represent that the motion of the particle in a simple harmonic motion is similar in a manner as the sinusoidal function. So, the kinetic energy of the particle K will equals to half mv square, where v is the function of time. So we can write here the same expression is half m omega square a square sine square of sine square omega t plus phi, or same expression can be rewritten as k equals to half k a square sine square omega t plus phi, because here we know k is equals to m omega square. K equals to m omega square. Let us take this expression as equation number 1. The expression 1 expresses that the kinetic energy of the particle executing the simple harmonic motion has a period of t by 2, the capital T by 2, means in a 1/4 cycle of the motion, its kinetic energy approaches from minimum to maximum or maximum to minimum. Also we know, as the concept of potential energy is concerned with the conservative forces. So for the particle which is executing a simple harmonic motion, since the force which is known as the restoring force for the simple harmonic motion is given by as restoring force in simple harmonic motion is given by restoring force as a function of time equals to minus k multiplied by the displacement as a function of time. Minus k multiplied by the displacement as a function of time. So if we consider this relation for simple harmonic motion, in that case, the potential energy of the particle executing the simple harmonic motion can be given by potential energy of the particle Pe equals to negative of the integration of force with respect to displacement with its lower limit 0 and maximum limit up to a position or the displacement in terms of x. So this can be given as 0 to x limit and integration as kx dx. That again can be rewritten as half k x square, which is the potential energy of the particle executing simple harmonic motion at any position of x with respect to its mean position. So if we express this displacement x as the time varying function, we can write here the potential energy of half k xt square equals to half k a square cos square omega t plus phi. Let us consider this equation as the equation number 2, which is for the potential energy of the particle. Again, you can see here that the period of the potential energy is also capital T upon 2, means half time period. So the total energy of the particle executing simple harmonic motion will be given by E equals to Pe plus Ke, the sum of potential energy and the kinetic energy, where we can write it here half k a square cos square omega t plus phi plus half k a square sin square omega t plus phi. On simplifying further, we get it half k a square, which shows that the total energy of the particle which is executing a simple harmonic motion has a conserved energy, because the value of k is constant for that particle, the value of maximum amplitude of the displacement for that particle. So the total sum of potential and kinetic energy will be conserved, or you can say the complete mechanical energy of the particle will be conserved throughout the simple harmonic motion. But just remember one thing, that we are considering the system as idle. It means we are considering that no additional or internal damping forces or friction forces are there. Thus, total energy of particle executing simple harmonic motion is independent of time. You can see here in the given diagram, the mean position of the particle is at the position O. Its displacement in positive direction is maximum up to plus A. Its displacement in the negative direction is maximum up to minus A. And with respect to its mean position, the change in its kinetic and potential energy are shown in the figure, where this curve shows the kinetic energy and the green curve shows the potential energy of the particle at any position. So that's all for today. We will continue in the next one. Thank you.